Let's say you have the standard string length function. Now someone gives you this function, which has totally different loop structure and control flow, and yet they tell you it performs the same computation but 4 times faster. Do you believe them? With our work you can, because these two functions are provably equivalent. We introduce a sound equivalence checker that operates directly on x86-64 binaries. It doesn't care what compiler you use, and it handles complex control flow transformations. We give it execution data in the form of traces. It finds a semantic way to align the traces of the two functions and attempts an automatic proof of equivalence. We show that our tool can handle control flow transformations like vectorization, loop unrolling, and loop peeling, as well as optimizations that don't change loop structures as implemented by modern compilers on x86-64. Come see our talk.
In our paper, Verified Compilation on a Verified Processor, we show in the tradition of building verified stacks how we have extended the KKML software development methodology down to a verified processor that we have developed. I will now show how one could use this development to reliably sort this year's PLI papers in alphabetical order by running a verified sorting program on top of our verified processor. Here we have collected the PLI papers into a text file. And by executing this command, we load the verified processor onto this FPGA chip and we load the compiled sorting program into this memory. And as a result, we get a list of sorted papers as output. We have also run other kinds of programs on top of our verified processor, in particular, as the paper title suggests, the KKML compiler itself.
Suppose you have a verified file system. It proves that if your computer crashes at any time, after running recovery, your data is safe. You write some innocuous-looking code using the file system API that atomically saves by first writing to a temp file, and on crash, you clean up by deleting the temp file. You want to prove this layered storage system correct, but it has two recovery procedures, which both have to run when we link the implementations together. Surprise! You've now left the territory of prior work. This is where our framework, Argosy, comes in. In Argosy, the developer proves each recovery procedure correct separately, and the framework has a composition theorem that shows the combined recovery is correct. Why would multiple recovery procedures be hard to reason about? The trouble is that the system might crash during recovery itself. When this happens, we have to start over from the bottommost layer. To see how our solution works, come to our talk.